Today's lesson is day 2 on sequences. Remember what we worked on the previous lesson? We worked on 2 different types of sequences, arithmetic sequences, and then geometric sequences. And just a brief reminder, sequence is just some type of pattern for numbers. There's many different types of patterns. Right now we're just focusing on these 2. Again, this word looks like arithmetic, but it's arithmetic. Air, like air you breathe, arithmetic. And then there's this one looks a little more like it sounds geometric. Arithmetic sequences always added or subtracted to get from one number to the next, from one term to the next term. And the geometrics always multiplied or divided to get to the next term. And again, these are just 2 different types of sequences. There's many other types, but we're just focusing on these for now. 8th grade standards. Here's what we're working on for the time being. Yes, the last lesson we did showed some different sequences, showed some examples. If you still need to review that one in terms of how we make the equation or the functions for them, definitely do so. I'm just going to show you a few more things today that can be helpful, just to more related to things we've been doing anyway with graphing and solving equations and things like that, and just show how it ties in. I'm also just going to remind you again, arithmetic sequences, they modeled like a linear function. So y equals mx plus b. And the m, remember, was actually, it's like the slope of the line when we graphed. You know, what something is changing by. What do you know? Same thing here. It's just the pattern that we see when we talk about an arithmetic sequence. And then b was the starting term. Okay? The starting term. And these, it was like a starting point for us when we were graphing, right? It's the y-intercept, a place to begin. Well, same kind of idea here, really. So arithmetic sequences is the very beginning term, whatever that may be. The geometric sequences, again, modeled with something that was nonlinear, those that were in intermediate, looks familiar. That's like an exponential function. It's that equation. F of x equals a times b to the x power. And just realize things were a little reversed in this one, right? A, this right here is the starting term. And then b, this one is the pattern. Because in this case, this part right here makes it multiply by some number or even divide by some number over and over as we look at the actual sequence. So, again, go back and watch the first lesson. Sequence is day 1 if you need to, but just kind of reviewing those main parts in terms of how we made a function or an equation when we found one of these sequences. Well, knowing how to write these is going to help us with different types of problems too, even when we have realized that we've been working with these types of sequences already. We just sometimes see them in table form and things that we're graphing, but we really have been identifying, okay, the different types of patterns that we've seen, and now just showing how that relates to linear equations, which again is the arithmetic sequences, which is these type. These are linear, and even if they're geometric, we can still write an equation for it. Now we've called it sequences in this lesson, but it's really just like writing an equation like we did in the past. Here's a table, right? We've filled in tables before and used those to graph and tried to find the slope like we've done, where we said, oh, how much is it going up by each time as we go on this side and as we go up on this side, and realize this is the same thing we were just doing with sequences. The y, our y values, this part more ends up being the sequence that we're looking at. And as I can see from this one, it's up 13, up 13, up 13, as the top is going up by 1, because we're going from one term to the next. So this, since it's adding every time, is like an arithmetic sequence. It's linear, I could think. And so I can make a function like y equals mx plus b. Well, it's 13x, right? Because I could even think of like a slope. It'd be 13 over 1, just going back to things that we've done very similarly. Y over x, 13 over 1 is just 13. And so, yep, it's 13x. And then my beginning term is like my y-intercept, 0.04, or in this case, it's 4. So, again, just kind of make the link that this is the same stuff. It's the same stuff as when we saw a table and we were trying to make an equation and found the slope, found the y-intercept. Well, sequences, really same idea. But you could see it with the table. You could see it with just if the numbers are by themselves, like we did a lot yesterday. This next one, we're going to start the same way we just did. We're going to look for a pattern. And as I'll get, again, it's a table, so as we're used to seeing, but concentrate on the bottom row here, and think of like we did with sequences just recently. What's the pattern? I noticed the top row already is going up by 1 because we've set that up, so it's going up by 1 every time. But the bottom, you can see, okay, it's going up by 8, ooh, up by 16, up by 32. So it's increasing by more than just the same number every time, so it's not arithmetic. But if I can find a pattern by multiplying, yep, it looks like it's timesing by 2, timesing by 2, timesing by 2. And again, I forget this sometimes, but that reminds me, oh, that's a geometric. So maybe even, especially with this one, write it to yourself just as a reminder off to the side. There's the equation, or if you have it somewhere handy, y equals a times b to the x. And a, remember, is the first term. B is the pattern. So these are y equals, or this one would be y equals 8 times 2, because that's doubling every time, to the x power. So there's a geometric one. Go to some of these other ones as well. A vertical table, same idea. Again, just like we've done in the past. I'm going to look for patterns here in the x side and the y side, right? The x coordinates, the y coordinates. So I see going down by 5. Ooh, that's going down by something different now. That's going down by 2.5. And then that one's going down by 1.25. So as I look at this next one, it's not going down by the same thing every time. So it's not subtracting the same number. It's not a linear then. But maybe I can see that it's going down by dividing. And yep, it looks like it's dividing by 2. Dividing by 2. Dividing by 2. Oops. And again, reminder, still important is the fact that it's on the other side. Dividing by 2 is the fact that it's going up by 1, up by 1, up by 1. Like, that's still important. Notice with our sequence, we're mainly just concentrating on the pattern on this side as long as it is going up by 1 over there. Then it's like the ones we've been doing here. Again, this is going to be a geometric, and since it's dividing by 2, remember there was kind of a trick to this. First of all, it starts off y equals, and then 10 is my beginning term for the geometrics. That starts it. So y equals 10, and then times, and how am I going to, I don't want it to be 2 inside the parentheses, because I want this to divide by 2 every time. So what can I multiply by that'll make it divide by 2? It's the fraction 1/2. So y equals 10 times 1/2 to the x power. And that last one. So again, first off, when you're analyzing these tables or analyzing these sequences, start by seeing, is it going up or down by the same amount? I think it's just easy to check adding or subtracting first. So first I look at this and say, oh, well, it went down by 10. And did it do that again? Oh, yep, down minus 10. Yep, down by 10, minus 10. As this side goes up by 1, up by 1, up by 1. So when I notice that, again, almost like a slope, right? Like the negative 10 over 1 if I was doing my slope and finding the linear equation, which is negative 10. So what do you know? This starts off as negative 10x. Just as a reminder, I'm just going to make this one a function. I'm going to call it a of x. Just that this doesn't change anything. It's still the same idea when I do function notation. A of x equals negative 10x. And then again, this, for the linears, this is like my y-intercept if I was graphing it, or for these, it's just like my starting term. Plus 109. So negative 10x plus 109. Another way to see, again, this connection, the sequences as we're working on, how it works, implies the linears, is I've got, again, just like something we've graphed in the past, a table here with some ordered pairs, and if I was looking at this like a sequence, let's say it was a problem that just had these numbers down below, and I was looking for a pattern, like I could say, oh, look, it's going up by 3, up by 3, up by 3 each time. As the top is going, the x-coordinates are going up by 1, up by 1, up by 1. Again, that would tell me that my slope would be 3 over 1, or just 3. And my y-intercept, I can see it in the table here again, which is 0, negative 4. There would be the two things that would help me make my equation. Y equals 3x minus 4, right? Again, but looking at this is just like the sequence stuff we're doing. So again, just trying to show you how it relates exactly to the graphing things we've done before. I could use those ordered pairs, and I could graph it if needed to be. 0, negative 4, 1, negative 1, 2, 2, and 3, 5. And then I could draw a straight line, or as straight as I can on here. Okay, pretty close, but I could see that would be a linear equation. And again, I can find the slope, and I can find the y-intercept. I see that the slope is up 3, right 1, up 3, right 1. Again, well, you know that's where this came from, that number, my x, my x-coordinate, my coefficient, I mean, with x, the slope. And then there's my y-intercept, 0, negative 4. But again, all this is just showing how those arithmetic sequences come from just like from linears. If I was looking at that set of numbers, and this was my pattern, -4, -1, 2, 5, ... It could be just like a sequence problem where I'm trying to identify the pattern every time, and I would get the same function when I write it either way. I'd still see it's going up by 3, and this is the beginning term. So just one more slide to show how it links to all of the things we've been doing. Last slide in this lesson, just as a reminder, as we've talked about, there are arithmetic sequences that we're looking at, there's geometric sequences that we're looking at, and those are just 2 types of sequences, but there's many other types of patterns or ways that we could look for a pattern with numbers and even be able to tell what numbers are coming next. But they just are different names for sequences, different types of them. So take a look at the numbers down below here, and we've got 3 other sequences. And you can maybe agree with me too as you look at these that, yeah, there's definitely a pattern to these sequences. Take a look at this first one. It says 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then ... This sequence, this is a pattern of numbers, right? And you could continue this sequence if you wanted and keep the numbers going, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we can definitely agree this is a sequence of numbers. It has a pattern. But if I ask you, is this an arithmetic or geometric sequence? Well, then you'd say no. It's just neither type. And I think some problems on today's assignment will ask you if it's an arithmetic, geometric, or just neither of those types of sequences. It probably has some name. We don't need to know it right now, but now you just have to recognize, oh, it's not one of the types that we're looking at. And why is it not? Well, this sequence is adding 1, but then it subtracts 2 to get back to the first number, right? Adds 1, subtract 2. Add 1, subtract 2, which is a pattern. But arithmetic sequences always add the same thing or subtract the same thing every time for the rest of the sequence. So this is just neither type of sequence. It's definitely a pattern. It's just not one of the types that we're looking at. Same thing with this next one. So this one goes, you can start seeing the pattern, goes from 2 to 5, which is up by 3. But then, just kind of looping up here, this one, notice then it goes back down by 1. Then it goes 4 to 7, it goes up by 3 again. Then it goes back down 1. Then it goes up by 3 again. And then it goes down 1. Is this a pattern? Is it a sequence? Yes, it totally is. But it's just not one of the 2 types that we're looking at. So if I'm trying to describe it, I'll just say it's neither of these 2 types. But it is definitely a sequence. And then this last sequence is just kind of a popular sequence, or one that's well known as you go on in mathematics, that shows up in different type of geometric figures and different types of nature. It's called, there's a particular ratio that follows this sequence. It's called the Fibonacci sequence. And maybe as you look at it ahead of me, you can even figure out how they continue to get the numbers, the next one and the next one and the next one, before I even say it. But if you take a look, it starts off with 1, 1, then it goes to 2, 3, 5, 8, 13, 21, 34, 55, and of course it keeps going on and on. And again, maybe you can spot it, but this sequence is also something that adds to actually get to the next number. What it does is it adds 2 numbers, and then that gets you the next number. So the first 2 numbers are 1 and 1. Add those together, and then you get 2. Then you look at the next 2 numbers, 1 and 2, and you add those numbers, and you get 3. 2 plus 3, the next 2 numbers give you 5. So you actually add the previous 2 numbers to get the next number in the sequence. 3 plus 5 gives me 8. 5 plus 8 gives me 13, and so on. And this is called, there's a mathematician that figured this out. He did other things too, but this sequence is named after him, Fibonacci. It's called the Fibonacci sequence, and again, it's one that shows up a lot in mathematics as you go and find common ratios for things. So the Fibonacci sequence is just another type of sequence. Again, not arithmetic, not geometric, but just know there's many other types out there like this one.